to discuss section of mechanics, which is the chapter called work, power and energy.
Sir, could you share the recording of the previous lecture?
Yes, I will share the recording and another copy of the notes, because unfortunately the notes that I've sent just now, that has got corrupted. So I'll just send it to you in a few minutes. Both the things, the recording and the notes, so you can refer to that. So previous lecture we had just done more questions and discussions on friction and Newton's laws in general. So going through will definitely help you in completing the exercises and solving problems yourself. Right. So I have started the recording. Yes. Okay. So let's begin. So we start with the definition of work, and in that we'll start with the discussion of work done by a force. So this is not the everyday meaning of the term work, which we take in some other context, in terms of effort or whatever like that, okay, or accomplishment or whatever. But this is a specific term in mechanics called work done by a force. So we will see that work done by a force is a scalar quantity, which is measured in something called joules. The unit of it is joules. So the first scenario in which we'll discuss it is that if a constant force, so by constant force, what do we mean? A force which is of constant magnitude and fixed direction. Okay, so by constant force, that is the meaning of it. It is of constant magnitude and fixed direction. So neither the direction should be changing nor the magnitude should be variable. So if such a force acts at a point, okay, which is displaced by S, by displacement S, then the work done by the force, which you can denote with the symbol W, by this force, okay, through the displacement of S is given by a simple definition, by the simple definition, which, as you might be knowing, is the dot product.
Sir, F into S.
It is F into S in a special case, beta, where the displacement is in the direction of the force. But what if the displacement's direction is different and the force's direction is different? Then we have to take the component of the displacement along the force.
Sir, can you kick out Bhavya 21 BRO 090421?
Well, that person is not in the meeting anymore.
Sir, he came yesterday also.
Sir, in sir's lecture mein also.
Okay. Fine. So what we will do is we will incorporate. Just a second. Anyway, just start by writing down this definition. I'll take care of it.
Sir, in the bracket you have written displacement S or R?
Just a second. No, that is S, beta. In the bracket also it is S. So displacement we denote with the symbol S. Displacement, you know from kinematics now what it means. It is the vector joining from the initial point to the final point. You know, where displacement होता है, the shortest path from initial to final.
Yes.
No, so that is a displacement. So like one of you, I don't remember who, but just now you said that work done is force into displacement. That is okay, but that is in a special condition. जब क्या हो रहा है, that force is in the same direction as the displacement. But here we are discussing a more general situation related to vectors when the force and displacement may not be in the same direction. Okay, I'll show you examples also. So as per the definition of work of dot product, we can say now that W is equal to Fs cos theta, where F is nothing but the magnitude of the force, okay, S is the magnitude of whatever displacement is occurring. But most importantly, theta kya hai? It is the angle between the force vector and the displacement vector. So now, for example, suppose this is something that is happening, that ऐसा मेरे पास एक inclined plane है or something like this, okay, and I've kept a block like this over here, okay, at the position E. Now what I do is to push this block along the inclined plane. For whatever reason, I start applying a horizontal force. I'm not applying the force along the inclined plane. I'm not applying it parallel to the inclined plane. I'm applying it horizontally. Okay. This is a physical example of how we will implement that definition. So a horizontal force of constant magnitude, let's say. Just a minute. Restart that program. Yeah. All right. So if we are applying a constant force, suppose the example, horizontally on a block like this. Acts on a block and it is displaced from, let's say, the point which I'm showing as E. So after some time it has reached this other position, let's say. So it's reached here. This block has during this time, as it is moving from A to B, block ka displacement kitna hai? The displacement is this vector. So to calculate the work done by this force, we'll have to calculate the dot product of this vector with the force. So the angle of inclination with respect to the horizontal is theta. You will see here that it will become Fs cos theta. So it will be less than F into S. Exactly, that's correct, Siddharth. Very good. Okay. So we can see that we can express this Fs cos theta or the dot product in two ways. We can either say it is the component of force along the displacement, which is F cos theta multiplied by the displacement, or we can say it is the force multiplied by S cos theta, which is the component of displacement along the force. So it depends on how we want to express it, but it's basically when we take dot product of two vectors, it is magnitude of one vector multiplied by the component of the second vector, which is parallel to this first vector. And we can take the first and second vector in any order because A dot B is equal to B dot A. So F dot S is the same thing as S dot F. So now when I do this vector operation aside, for example, if I want to express it that way, I can see here that the force vector and the displacement vector, they are at such directions, you can see from the diagram, that the angle between them is theta, because the force is horizontal and the displacement is along the direction of the inclined plane. So because the inclined plane is at theta to the horizontal, so that means force vector or displacement vector के बीच में भी जो angle है वो कितना है, that is theta only. If I take this force vector aside, it's like this, and then I draw the displacement vector from the same origin, you can see that displacement of force के बीच, the angle is the same as the angle that is there between the inclined plane and the horizontal. Okay. This angle theta is the same. So work done will become here F dot S. which by definition is Fs cos theta. Now we can think of this as, F into S cos theta, or we can also think of this as F cos theta into S. It doesn't make any difference, but the interpretation is slightly different. अगर मैं S cos theta देखता हूँ यहाँ पे, what is S cos theta? If this is the force F, this component of the displacement is S cos theta. The component of that displacement vector along the direction of force, that will be my S cos theta. So displacement vector actually kahan pe, it's like this. But if I draw a component of that along the axis of force, that is S cos theta. So it is force multiplied by the displacement along the direction of force. Or on the other hand, I can do one more thing. I can instead take the component of force along displacement, which is F cos theta, and multiply that with S. That's also one and the same thing.
Sir, in every case, it is the same only, in the sense means any one of the individual will have cos theta.
Okay, Ethan, you can see the screen now, no, clearly. Okay, yeah, sorry, I just missed the last question. Somebody was asking something. I was interrupted. Sorry.
So both the cases make the same thing, no? Because in every
Yes.
case, any one individual will have cos theta.
Yes, Krish. Both of them mean one and the same thing. No, but so whether we take the component of force along displacement and multiply it with the magnitude of displacement, or we take the component of displacement along force and multiply that component with the force's magnitude, it's one and the same.
Sir, component of force along displacement is F cos theta into S, no?
Yes. So the other thing I can do is instead I let the displacement vector be the way it is. I don't disturb the displacement vector, but instead take the components of force. So compared to my displacement, the force is at what angle? It's at theta. Okay. So अभी force का मैं अगर component लूँगा along this direction, तो ये component कौन सा हो जाएगा? Cos component हो जाएगा, और दूसरा component sin हो जाएगा. Okay. So F cos theta into sin will give me numerically the same result as F into S cos theta, na? So F cos theta into S will give me the same thing as F into S cos theta, na?
Yes, but their interpretations are different, no?
No, so that is the thing, na? They are one and the same thing. That is why A dot B is equal to B dot A. Now, that is the relationship that two vectors have. You understanding my point, Bhatta?
Yes, sir.
Now, the dot product of two vectors A and B is such that it is the same thing whether I multiply A's magnitude with B cos theta or I multiply B's magnitude with A cos theta. It's one and the same thing. It is one vector into the component of the other, which is parallel to this. Okay. So that is why we can say that we can further, interpret this with two statements, that it is force into displacement in the direction of force or component of force along displacement multiplied by displacement. It's one and the same thing. Whether we classify it like this or we classify it like this is one and the same thing. And that same thing is basically what the dot product. So the proper technical way of defining the work done is that it's a dot product. So dot product itself means both these things.
So your voice broke.
So this is the definition of work done by a constant force. Yes, internet connection. It should be clear now again. Okay, so the unit, the SI unit of work done is joules. One joule is equal to 1 Newton meter. The dimension of the quantity work done is the same as the dimension of force into displacement. So it is ml squared t minus 2. Yes, I will be resending Sakshi. I'll be sending the recording as well as the notes because that file has got corrupted. Okay, so anyway, now for the moment, definition of work done by constant force. This is clear, I hope. Okay. Now here I'm emphasizing that for this definition to work, the force should be constant. Okay. So like in my above example, suppose the force I'm applying is 10 newtons and the displacement is some 5 meters and the angle theta is, let's say, given to us. So the angle of theta is 60 degrees or something. So let's take in this example. Suppose the magnitude of the force is 10 newtons. The magnitude of displacement, let's say 5 meters, and theta is equal to 60 degrees. Then work done here will become how much? So the work done will become 10 into 5 into cos 60. So it will be 25 joules. Now let's do one more thing. In the same question, the same situation above. If mass of the block is equal to 2 kilograms and g is equal to 10 meters per second square, find the work done by the weight of the object. Weight is a force which we call mg, or it's of magnitude mg. So let's find out the work done by the weight, and let's also find the work done by the normal reaction force. These are two other forces which are acting on the body. So let's find these.
So what is the displacement?
The displacement is 5 meters. That angle is 60 degrees. Okay, this over here.
Sir, same force.
Sorry, come again.
Sir,
Yes.
so the force is 10 newtons only.
Yeah, that force F,
Oh.
the external force, if you are applying horizontally, that is 10 newtons. So work done by this force is work done by this force is 25 joules. Okay. But now, how much is the work done by mg, the weight of the object, and how much is the work done by normal reaction?
Work done by mg is 50 joules.
Okay, what is the angle between mg and the displacement? mg
60
is
degrees.
acting vertically downwards, isn't it?
Yes, sir.
So what kind of angle is there between displacement and mg? Is it an acute angle or obtuse angle?
Acute.
नहीं बेटा obtuse होगा. हाँ. It will be 90 plus 60. mg is acting vertically downwards, na? And see the displacement is along the inclined plane. isn't it? So work done by mg will be of what type? Positive or negative?
Negative.
It will be negative. Yes.
Sir, what have you written in that note that W bracket is equal to F bracket, S bracket, and below that?
Sorry, which one? SI unit of work done is joule. SI, standard international.
Yeah, sir.
That 1 joule is equal to 1 Newton meter, and dimension of work done is equal to dimension of force into displacement. You have done the chapter units and dimensions in your college lecture.
Yes, sir.
So that one, na? Box bracket में क्या होता है? Dimensions होता है. So I'm expressing the dimensions of work done in terms of the fundamental dimensions, MLT. Na? So it's how much ML square T minus 2. Understood? Na?
Okay, sir.
उसके पहले क्या है? 1 joule is 1 Newton meter because basically what? Force into displacement. Na? So 1 unit of work done क्या होगा? It will be 1 unit of force multiplied by 1 unit of mass. 1 unit of displacement, right?
Yes, sir.
So SI unit क्या होगा? It will be Newton meter. So 1 Newton meter is equivalent to what we call 1 joule. Joule is the special name given to the SI unit. So it is equivalent to what? 1 Newton multiplied by 1 meter. Okay, so anybody got the answer for work done by mg? Krish, you will have to modify your answer with that. The angle between mg and displacement is not 60 degrees, no? It is a obtuse angle. Your second answer is correct. Good. Okay, but the first answer it should come as a negative quantity. Okay, so I'm just making the diagram again. So displacement is at 60 degrees to the horizontal. So let's say displacement is this vector. This angle is 60 degrees. But in comparison to that, what is the weight? The weight is a vector which is acting downwards. No? So weight to ऐसा है. mg. Its magnitude is how much? 20 newtons, I think. We take an m to be 10 kgs, sorry, 2 kgs. So what is the angle between these two now? This angle theta. Theta is 150 degrees. So work done by weight W. This dot product. Okay. So it is mgs cos theta, where theta is now 150 degrees. So cos theta is minus root 3 by 2. It is 20 into
So it is scroll down.
okay. So the mass was 2 kgs, so like this. Okay. Whereas now if you look at the normal reaction, the तीसरा force है, that's acting like this. It is acting perpendicular to the displacement. So work done by normal reaction that will become how much now? It will be 0. Cos 90 is 0. So
Sir, your
what
screen is stopped.
is it visible now?
Yes.
Okay. Good. So work done by normal reaction that is the dot product of normal reaction with the displacement. Now, normal reaction is acting perpendicular to the direction of displacement. So it's 0. So gravity is doing negative work in this case, normal reaction is doing 0 work. Whereas the force F which we applied horizontally, that was doing positive work. So what we are learning from this is that the work done by a force which is the formula for work done by a constant force can be positive, 0 or negative depending on theta, the angle between the force vector and the displacement vector. Okay, people, so I hope this example is clear to everyone. Any doubt? Okay, now we will look at a more interesting situation. Now, it could always be like this, that while the body is moving, the force could be changing. It may not, we may not always have a constant force. Now, a good example of that is spring force. If you push a block against a spring jitna compress ho raha hai, the amount of spring force that it applies, the tension in the spring, that goes on increasing. So as the spring is getting displaced, or as a body is displacing a spring or causing it to compress or extend or whatever, the magnitude of the spring force is doing what? It is changing. So that's an example of a variable force. Okay. Similarly, there are other forces in nature, like for example, if you talk about frictional force. Okay. Now imagine a body sliding on a surface, on a rough surface, horizontal surface, and it's sliding along a curved path. It's going zigzag or curved or whatever. So जैसे उसका direction of motion change होगा, accordingly the direction of kinetic friction will also be changing. So that's an example of a force whose direction is changing. So in general, both the things are possible, that a force can be variable both in terms of magnitude as well as direction. So in that case, how do we calculate the work done by a force? Okay. So this is like the more general definition of work done, because we will cover variable forces also in this. So work done by any force F. So this covers the case where F may be a variable force also. Maybe constant also, it may be variable also. And when we say variable, it may vary in magnitude and or in direction. So it covers all types of forces. It covers constant forces, it covers forces of constant magnitude but variable direction, or reverse, forces of variable magnitude but constant direction. All this is covered within this. Okay. Sorry?
Your voice was cracking.
Okay. The audio is clear from my side now. Okay, so what happens here is that if a body is moving along a general path like this, and as it is moving, there is some force acting on it. So by the time the body is here, or the particle is here, the force has maybe changed, both in terms of magnitude and direction, like this. So how do we calculate the total work done as the body is moving from some initial position A, let's say, to some final position B? So what we have to do to calculate the work done is that we have to first find out that during a small part of the journey, if the displacement is a very small value ds, okay, so then what we do is for a very small displacement, ds. So because it's a very small displacement, during that small displacement, the force is a constant value. The force might be changing from time to time, but for a very short interval of time, the force is more or less constant. Okay, so during that very small displacement ds, the work done by the force will be a very small amount, so we'll write it as dw, and that is F dot ds. So therefore, for the entire motion from, let's say, A to B, the net work done, that will come by integrating this. The integration of F dot ds from A to B. So by this definition, we say that work done is the path integration of force over s or displacement. So this we can now say is a general definition of work done. This will apply to all cases, whether the force is constant or variable. And in terms of variable, whether magnitude is changing or direction is changing or both are changing, it will always apply this formula. Okay. And we'll also see that if the force happens to be constant, that both magnitude and direction are constant, then this formula automatically reduces to F dot S. This only becomes F dot S because force is constant. Okay, so let's understand this with an example.
Sir, just 1 minute.
Okay.
Okay, sir, done.
So one second.
Okay. Okay, done.
No, sir, last slide.
Okay, so let's look at an example question now of work done by a variable force. Yeah, but before that, we'll note down the important thing that for the formula, the general formula, work done by any force, this is the general formula or definition also you can call it, because it defines work done as the path integration of force over displacement if the force happens to be constant. Then we can see that work done, which is integration of F dot ds, will automatically become F dot s. So this particular case, this is a special case of the general definition when the force is constant. So actually the proper definition of work done is no longer, that class 9-10 type of definition that we know, that it is force into displacement in the direction of force. The proper calculus definition of work done, or the proper mechanical definition of work done now, is that it is path integration of force over displacement, F dot ds integration. And that is why it reduces to F dot s if the force happens to be constant. So this is a special case definition that it is F dot s. In general, the definition of work done is that it is integration of F dot ds, or it is the path integration of force over displacement. Okay, so now let us understand the application of this for an actual variable force with a numerical situation. Let's see an example in which we are looking at a 1D motion with a variable force acting. So now in my example, let's say a block is initially at the point A where its x coordinate is 1 meter, and after some time from here it is moving to the point B where its x coordinate has become, let's say, 5 meters. But during this motion from A to B, there is a variable force acting on it. Direction is always along the x-axis, but the magnitude varies with the x coordinate. So this is our x-axis. So F is a force of variable magnitude acting along the x-axis. So it's acting along the positive x-axis such that the magnitude of the force is equal to kx, where k is 20 newtons per meter. So k is a constant, it has a magnitude of 20 newtons per meter, and x is the instantaneous position. What we have to do now is we have to calculate the work done by this force from A to B. So you will see this is a somewhat simplified application of the above definition, f dot ds integration. Why I'm saying somewhat simplified? Because we solve the dot product f dot ds for any small displacement ds between A and B. The direction of force and displacement is the same. So that dot product will result in cos 0, which is 1. So from dot product of f dot ds vectors, it will become f into ds, magnitude of force multiplied by magnitude of small displacement. And that we'll have to now integrate from the initial position A to the final position B to get the net work done. Okay, Siddharth, I'll just verify the answer. So it become 10 into 25 minus 1. Yes, very good. Correct.
Sir, we will solve this question using that integration one, no?
Yes,
Integration
you
of
have to
f
solve
over
it
ds.
using the integration. Okay, but when you first write the integration, you have f dot s and ds vector. So you have to first solve that, that dot product. So now you can see what is the direction of displacement. It's along the x-axis only, and what is the direction of force? That's also along the x-axis. So that f dot ds dot product of two vectors will become a simple dot product of f into dx, where f is the magnitude of the force and dx is the displacement which is happening along the x-axis. So you'll end up integrating f dx, simple product, not dot product. From the initial point where at x at E, the x coordinate is 1, to the final at B, where x coordinate becomes 5. This is our
Sir,
x
what is the
axis.
value of f?
Somewhere here is a point E. It was kx, where k is 20 newtons per meter. This is x equal to 5. Now at any general point, when the body is here at x equal to x, the force acting on it is kx in magnitude, and now the small displacement it makes from here to the next. You can see kx I cap. Its magnitude is kx, its direction is along the positive x-axis. Displacement in vector form can be written like this. So it's like this. So both of these are along positive x-axis. Okay. So therefore, the quantity f dot ds is just becoming this, which is just becoming kx into dx. So therefore, work done by the force, which will be integration from A to B, will become ultimately integration of kx to dx from A, where x was equal to 1 meter, B, where x is equal to 5 meters. In this case, a constant which is 20 newtons per meter is given to us. Okay. So from this, we can calculate the work done. So it should come out to be 240 joules. Okay, so one more step involved here. Constant k comes outside. Integration of x dx is x squared by 2. So that's how it becomes. Now substitute k. So 10 into 24 or 24 joules, 240 joules.
So,
Yes.
why did we take ds as like dx? Can't we take it just directly 4 because it's a straight line path?
No, better, that's fine. But the thing is, see, we are going to calculate the dot product of f dot ds and integrate it. Na? So usme the force is variable. Na?
Yes, sir.
Force is not uniform at every point, right?
Yes,
Okay,
sir.
so we cannot directly take f dot s. You understanding, na? So it is correct to say that the displacement is 4 I cap. But what will I do with the displacement? Because I cannot use the formula f dot s over here, because the force is not constant. I have to use the proper phase integration. So that's why we cannot directly write the displacement as 4 I cap and take dot product here. We have to do the integration. It's not to do with the displacement being 4 I cap, it's to do with the fact that the force is variable.
Okay, sir.
Is the point clear, beta? Yes, no? Okay.
Yes, sir.
So this example clearly demonstrates how we calculate work done by a variable force using integration. Albeit in this case, the force's direction is constant, only the magnitude is changing. Okay. So let's come to another example next. So any doubt in this example, anyone? Is clear? Okay. So next example, we'll take a somewhat familiar example in terms of what we've learned in mechanics before. So this time we will take a situation like this. What we are doing is that there is a smooth horizontal surface on which a block is placed, but on the other hand, the block is also attached by a spring. In fact, let's do one thing. Let's take a rough surface. So friction will also come into play. Okay, so now with the spring, we've attached certain block of mass m, and this is a rough surface. It has a given coefficient of friction. Now, initially, the spring is at natural length. It's not. So this is initially when the block is at the position here. Now we start pulling the block with a constant external force F. Just a minute, people. I'll have to reshare the file. Just give me a moment. Yeah. Yeah, it should be back online now. Okay. So now what we are doing is we are applying a constant horizontal force like this on the block. So given that the mass of the block is 5 kilograms, take G as 10 meters per second square, take the coefficient of friction as 0.1, okay, and take the spring constant as, let's say, 20 Newton per centimeter. Okay. Now, initially,
Sir, 20
block-
Newton per centimeter. That's what you've written.
yes, yes, N per cm. Okay. So initially, the block is at a position such that the spring is at natural length. L. Now a constant force starts acting on it. Of magnitude 10 Newton is on the block. Let's make this force large touch at the block. Okay. The spring force friction gravitational force and normal reaction. Want to find the work done by each of these. for a displacement of 2 centimeters. So as the block displaces through 2 centimeters, you want to find the work done by each of these forces. The external force F, which we are applying horizontally and of constant magnitude, 45 newtons on the block. The spring force that the spring is applying on the block. Okay, now we'll discuss a little bit about spring force also before we sit down to solve this problem. Okay, so let's work out each of these now. So let's start with the work done by force F. That's very simple. That's a constant force that is acting. Okay. And the displacement of the block is along the same direction as the force. If we are horizontally displacing it. The displacement's magnitude is 2 centimeters. Its force's magnitude was 10 newtons. And the angle between them is 0. So work done by F will just become 0.2 joules. This was a simple part. Now let's come to the work done by the spring force.
Sir, one second. How do you know F is 10 Newton?
Sorry, how do we know? That was given in the question. That is part of the data given in the question. Okay. Oh, sorry, 45 Newton. Right, corrected it to 45. So anyway, so it will become 45 into 0.2. Sorry, into 0.02. So that will become how much? 0.9 newtons. Right. This much work is being done. This much. Now let's come to the work done by spring force. Now the spring force has a special property that the magnitude of the spring force is kx, but the direction is opposite to the displacement. Okay. So here this shows us that when a spring is at natural length, L is called the natural length, the spring force is 0. When the spring is relaxed or at natural length. But suppose we take the block from that situation to a displacement of positive x such that the spring is getting stretched now. Then it applies a force of minus kx, minus showing that the direction is along the negative x-axis. So we displace the block from here by x. So now the spring becomes in what we call extended state. It's extended. or it has an extension of x. So it applies a force like this. So for an extension of x, the spring force becomes minus kx. Minus is just showing us that the direction of the spring force is opposite to the displacement or opposite to the extension. So here K is called the spring constant. And it is a physical property of the spring. So the spring constant should be expressed in newtons per meter. SI unit is Newton per meter. Okay, so this is about spring force. Now, how we'll calculate the work done by the spring force? To calculate work done by the spring force, you have to see that at some instant, if the spring is in this state that is extended by x, so then on the block, what is happening? The spring force that is acting, that is equal to kx in magnitude but opposite in direction. So now if the block makes a small displacement from here to here, small displacement
Sorry, your voice is cracking.
Voice is cracking.
what is the work done by the spring force during that? Okay, but the internet, just wait a second. Okay, let's try it again. Is it all right now?
Yes,
Yes,
sir.
sir.
Now,
Okay. Okay, so what is happening for a small displacement dx, where we are stretching the spring further from x to x plus dx, how much work the spring is doing? It is doing negative work of minus kx dx, because the direction of spring force is opposite to the direction of displacement and the magnitude is kx. Okay, this point is clear.
yes, sir.
So now for the total displacement that is happening, where we are taking the spring from natural length till it is extended by how much? It is extended by 2 centimeters, because we are displacing the block by 2 centimeters. Okay. Total displacement of the block is going to be 2 centimeters. So we are going to go from the initial state where the spring is at natural length, so x is equal to 0, to a final state where x is equal to how much? 2 centimeters. So total work done by the spring force that is going to be integration of minus kx dx. But from the initial state where x was 0 to the final state where x is equal to 2 centimeters. So this will become minus k into x square by 2. But from x equal to 0 to x equal to 2 centimeters. So the work done by the spring will become minus k by 2 into 2 into 10 raised power minus 2 whole square. Now I'm converting to meter square. Minus 0. So k is in Newton per meter, and this x square that we've written is in meter square. So we'll get the work done in joules. So k was given to me as 20 Newton per centimeter. So we'll convert that. That becomes 20 into 10 raised power 2 Newtons per meter. This is the SI unit value of k. So this is in Newton per meter, this part. And this is now in meters square. So I'm getting the whole thing in what? I'm getting it in joules. But the work done by the spring will be negative because spring force is acting in the opposite direction to displacement. So as you can see, this will become minus of 4 into 10 raised power minus 1 or minus of 0.4 joules. That is the work done by the spring. So two of the things we found out now. Work done by the external force which we apply horizontally, that is 0.9 joules. And the work done by the spring force which is minus 0.4 joules. Okay. Now you have to also calculate the work done by friction, the work done by weight, and the work done by normal reaction, all these other forces. So I'm just minimizing this a little, and also hopefully you can see part of the data of the question.
So where did that minus k by 2 go?
वैल्यू सब्स्टिट्यूट क्या है उसका k का वैल्यू सब्स्टिट्यूट क्या है यहाँ पे कितना था 20 न्यूटन पर सेंटीमीटर सो उसको कन्वर्ट किया न्यूटन पर मीटर में और सब्स्टिट्यूट किया ओके
ओके सर ओके समझा समझा
Hey, but I use the frictional force will be dependent on what coefficient of friction no? And normal reaction. So spring force कैसे act करेगा? It will act opposite to the direction of displacement, and its magnitude will be how much? Mu n, and the normal reaction will be how much? Mg over here. So coefficient of friction is given to us 0.1, and the weight of the object is how much? It is 50 newtons. So the friction is 5 newtons in magnitude. Okay, so next thing we need to do here is calculate the work done by friction.
So in friction only the Force part will change, no? Displacement part will be the same.
Yes, displacement is the same, and now friction's work done will be easy comparatively, because what is happening, what kind of force friction is here? It is a constant force, no? It's not changing magnitude or direction. As the body is displacing, okay, neither the magnitude nor the direction of friction is changing. So we can use the dot product definition. So friction kitna hai? Mu n hai, and n is equal to mg. So when you look at the free body diagram at any point of time now of the force of the block, you will see what all forces are acting on it. External force, this was a constant force. Okay. Then there was spring force, this was a variable force. This was a variable force, so we had to use integration for this. But the other forces are also constant. Friction, that will be mu mg in magnitude, the weight mg, and normal reaction. And that's why the block has an acceleration in this direction initially, because F dominates over spring force and friction, and that's why it displaces like this. Okay. But anyway, here we are not interested in the acceleration, we are interested in the work done. So work done by friction will be simply equal to minus of friction into displacement. So minus of mu mg into S. So that is minus of 0.1 into 5 into 10 into 2 centimeters. So this is becoming 5 joules into, so it will be minus 0.1 joules. This will be the work done by friction. Okay. And now the other two are very simple. What about normal reaction and mg? How much work they'll be doing here?
So normal reaction should be 0, no?
Exactly. And what about mg? Will be
So
0.
mg also 0.
Also 0. Right? So those two forces are not doing work. Why? Because they are acting perpendicular to the displacement. So we don't need to even do any calculation. We can see that since normal reaction and mg are both acting along the vertical line, one downwards and one upwards, whereas the displacement is happening horizontally. So the work done by these two will be 0. So work done by normal reaction is 0. Work done by mg is 0 because the displacement is horizontal. And these forces are vertical forces. So importantly, in this example, through the definition of work done by variable force, we have also learned a little bit about spring force. What we have learned is when a spring is extended, now uska natural length L hai, and we have extended the spring or stretched it by a distance x, what kind of force acts? The magnitude of force is kx, and the direction is opposite to the extension. Now we'll see also that the spring has a similar behavior when you compress it. When you compress it by x, the force again acts opposite to the compression, and it is of magnitude kx. So on either side of the natural length position, whether we compress it or we extend it, the spring applies something called a restorative force. That means the direction of the force is opposite to the direction of the displacement or the deformity given to the spring. Compression or extension is also called deformation because it's deformed or is changed shape from the natural position. So whichever direction in which we are deforming the spring, the force that the spring will apply will oppose that. So we call it a restorative force because the spring tries to restore to the natural position.
Sir, why didn't we use that integration method in friction?
We didn't need to because friction is a constant force. देखो जनरल डेफिनेशन क्या होता है वर्क डन का F डॉट ds इंटीग्रेशन, बट अगर मेरा फोर्स कांस्टेंट है देन आई कैन रिड्यूस टू F dot s. Okay, so if force is constant, then
Sir, so spring force isn't constant force?
Spring force is not. Spring force is the only one which was variable out of these forces. That's what I'm showing you in the FBD also here. That's important. That only one of the forces is variable, the spring force, because it depends on x. The others are all what? Constant forces. So normal reaction, F, weight and friction, these are all constant forces. This is kinetic friction. Whereas the spring force, with proper sign, it is in fact minus kx. Its magnitude is kx. This is the one which is the variable force. So for this one, we have to use integration.
Okay, sir, understood.
Okay, people. So hope this example was clear to all of you. Okay,
Yes.
now very good. Okay, now next we will look a little bit more in detail about spring force before we come to more examples of application of definition of work done. And then work done is of course only one part of the chapter. We will also discuss about energy. We'll discuss about two types of mechanical energy. One is kinetic energy and that the other is potential energy. So all that will come as we move along in the chapter. Okay. So, but first let's discuss a little bit more about spring. So we'll discuss in terms of spring force first. And at a later stage, we'll also discuss something called potential energy of the spring, which you might have heard about, elastic potential energy or spring energy. So the spring has a property called elasticity. Just like a rubber band, it has an elastic property, which is basically a property whereby it tends to always retain its natural shape. Okay, and how it tends to do is by applying something called restorative force, which in language of mechanics we can also call as tension. Natural shape. In the case of the spring, we'll just call it the natural length. Natural length or the relaxed length or the relaxed state, you can say. So it always tends to retain its natural shape by applying something called restorative force. Hence the name restorative, because it tends to restore itself back to the natural shape. So for example, if this is a spring whose natural length is L. Then from this natural length, if we extend it by pulling it by two forces in the opposite direction, you'll see that to keep it extended, we have to apply an outward force. On its own, it will not remain extended. We'll have to keep applying an external force, because the moment it is extended, the spring will now apply what we call the restorative force. So T over here is the tension, which is basically the restorative force applied by the spring. And it applies this because of its elasticity. Okay, due to its elastic nature, or what we call its elasticity. Okay. So this elastic force has a magnitude which is proportional to x. Okay. So that constant of proportionality is called the spring constant. Now in this case, it is, I'm showing you what is a state of extension. Okay, here the spring is extended, so it is in a state of extension. Okay. But the same thing, we can also apply a force in such a way that the external force is applied inwards. That is creating a compression in the spring. So now this could be like this, where we have compressed the spring by x distance. So its length has changed to L minus x instead of L plus x. But to do that, we'll have to apply the external force inwards now, because it will have to oppose the spring force, which will be acting in which direction? It will be acting outwards now. The spring will apply an outward force. So here F will have to be equal to T. But again, T is the tension, which is acting in a restorative manner, whether it is this example or this example. Okay. So both compressed state as well as elongated state, the spring applies a restorative force. So with sign convention, we write this as minus kx to show that when x is negative, that is the spring is getting compressed, the force is positive or it's outwards. And when x is positive, that is the spring is elongating, the force is inwards. Okay, the spring force, that is not the external force, the spring force is inwards. So with sign convention, we write this spring force as, or the restorative force of the spring as minus kx. So restorative force of a spring with sign convention. The above equation is not with sign convention. There just the magnitude of the tension is given. Is given by the formula minus kx, where k is the spring force.
So could you please explain that restoring force again?
Yeah, sorry, come again, beta. What was the question?
So could you please explain that restoring force again?
Restoring force, and why we call it, because it tries to restore the spring back to natural length. See the first of the three diagrams. Okay, if we are not applying any external force on the spring, it has a natural shape in the form of a natural length. Now from there, for example, if we elongate the spring by applying outward force, the second diagram. So how the spring is reacting to that elongation? It is applying a restorative force inwards. Now the direction of the tension in the spring is inwards, so it's trying to restore it back. That's why it is called a restorative force. Understood?
Yes, sir.
Similarly,
Yes,
from the natural length, now again from the first diagram, instead of extending it, if we want to compress it, then to go from the first state to the third state over here, what we'll have to do? We have to apply an external force inwards. So why we have to apply external force inwards? Because the spring on its own is opposing that by applying a restoring force or a restorative force outwards. You understood now?
yes, sir.
So
But
instead
then,
of,
sir, like, it
yeah,
should be kx minus kx by 2, right?
minus k, nahi, beta, it is equal to kx. The magnitude of the force is equal to kx. Okay, so both
But
ends
sir,
of
we're
the spring.
applying force from both the sides. Then, like, there's a displacement of x if we
No, no,
just
see,
measure
see
from
that,
both the
see,
sides.
this is what you have to understand. That is the property of the spring. Spring में जो tension develop होगा ना, that tension is proportional to the amount of change in length. It is not proportional to the displacement of the end of the spring. It is कि उसके total length में कितना change हुआ है. तो
Okay, sir.
you know the length has changed from L to L minus X or L to L plus X, whichever be the case. So the tension developed will be proportional to that X, which is the change in length.
Yes, sir. Got it.
Understanding my point? So for example, here I have shown you a situation where you are applying force from both the sides. Now this is also equivalent to a situation where suppose I have attached the spring to the wall on one side and now I'm not doing anything to the other side. So it will exist at its natural length. ठीक है? But अभी मैं अगर दूसरे side से pull करने लगूँ उसको तो क्या होगा? Now you'll see this point's displacement only is x, whereas this point is remaining the same. But that doesn't matter so much. What matters is कि स्प्रिंग के टोटल लेंथ में अगर x का एक्सटेंशन आ गया है तो मुझे यहाँ से भी फोर्स कितना लगाना पड़ेगा kx के मैग्नीट्यूड का और वॉल यहाँ पे रिएक्शन फोर्स लगाएगा टू बैलेंस द इंटरनल टेंशन. सो दिस विल बी इक्वल टू kx. Understood?
Yes, sir. Thank you, sir.
Yeah, so similarly to compress the length by x, I'll have to apply a pushing force from this side, and on the other side automatically the wall will also apply a pushing reaction force now, and that will balance the restorative force or the internal tension of the spring. So that only when we write it with sign convention, we write it as minus kx to show that whatever is the direction of x, uske opposite mein force act karta hai. So if x is outwards because the spring is extending, then the force is inwards. Whereas if x is inwards because the length is decreasing, then the force is outwards. So that is the meaning of the term restorative. So that minus sign captures that statement that it's a restorative force, which is proportional to displacement or proportional to the amount of deformity. Okay, so this is about spring force. Now we'll see more examples of application of spring force, both in terms of work energy problems later, as well as when we do some revision problems in Newton's laws later. Also we'll see situations where spring force comes into play. So there we have to treat the tension in the spring just like we would treat the tension in a thread or a wire, but the difference is the spring is of variable length. Okay. All right, now let's look at another example problem. So this time what we are doing is we have a smooth surface on which we have a block of mass m like this. Now this is, let's say, again a rough surface. So it has got some coefficient of friction mu. So coefficient of friction is 0.2. Mass of the block is, let's say, 10 kilograms. G is 10 meters per second square. Now what we're doing is we're applying an external force, but we are applying that force at some angle. It's not acting. We are applying an external force like this at an angle theta to the horizontal. So a constant external force of magnitude 50 newtons, okay, acts at theta equal to 37 degrees as shown. So find the work done by each of the forces when the block moves by, let's say, displacement of 10 meters. Okay, so we are applying the force at theta to the horizontal, okay, and it's on a rough surface. Mass of the block is given to you, so we know the weight. Okay, now when we apply this force horizontal, at an angle theta, assuming that the block displaces, that means we are able to overcome friction, which seems likely, okay, because coefficient of friction is only 0.2 and the magnitude of the force is 50 newtons. So definitely we are overcoming friction. So we have to find out how much is the work done by each of the forces acting on the block by the time the block displaces by 10 meters horizontally. So magnitude 50 newtons. And the displacement of the block is in which direction? Horizontally. And it's of magnitude 10 meters. So the angle between these two is 37 degrees. So the work done by this constant force, we calculate just as F dot S. So it will become 50 into 10 into cos 37. So it will become 400 joules. This is the work done by this force F. Now similarly, I want you to calculate for me the work done by all the other forces. So how many other forces are acting? Let's find out from the free body diagram. So there is weight of the block acting vertically downwards, pretty large amount of force, 100 newtons because M is 10 kg. Then there is some kind of normal reaction acting on the block, it will be vertically upwards, which you need to calculate how much is. You have to calculate how much this normal reaction is. And last of all, there is kinetic friction acting because the block is sliding. There's kinetic friction, which is equal to mu n magnitude. So we need to calculate how much that is also. So kinetic friction कितना है? Mu n. और n के लिए क्या करेंगे? We have F sin theta plus n is equal to mg, because this block will be accelerating. whereas F cos theta minus friction will be equal to MA, and the kinetic friction is mu N. So we can see normal reaction is mg minus F sine theta. So that is 100 minus 50 into 3 by 5. So 70 newtons is the normal reaction. So kinetic friction is 0.2 into 70, 14 newtons magnetic. So work done by friction will be minus of friction into S. So minus mu n into S. So that will be minus of 14 into 10 and not minus 200, because that is the thing you have to be careful about in questions like this. And don't forget your basics from Newton's laws, that if the force is acting at an angle, it affects the normal reaction. No? So it affects the friction. The friction is not going to be mu mg, it is going to be mu something less than mg, because normal reaction is less than mg. So this is work done by friction. Okay. And what about the work done by normal reaction? That will be 0. And work done by mg, that will also be 0, because n and mg are perpendicular to the displacement. Okay, people, so hope this question is clear.
Sir, one second. Could you please explain the work done for friction? Because I'm getting a different answer.
Work done by friction, ना देखो friction का magnitude कितना है mu into normal reaction, है ना? और normal reaction का magnitude
Yes,
कितना है वो मैंने यहाँ पे निकाला है from the
MG,
body
which is
diagram,
100.
ना? This one, this equation. So the normal reaction is not equal to mg, it's less than mg. Instead of 100 newtons, it's 70 newtons. Just a second.
Oh, okay, wait, sir, I understand. Never mind, sir. We'll do that now.
Okay, so the reason
Sir,
we
one
have
more
taken
doubt regarding work done by friction.
tell me.
So, like, wouldn't you then multiply, see, like mu n s cos 180, something like that? But you're not
वहीं से
taking
तो minus
cos.
sign आया ना बेटा. Cos 180 है, that's why the work done is negative, ना? That's why it is minus of mu n into s. Got it, na?
So I thought the friction was negative.
No,
Okay.
So see this term, if we write it properly first, it is minus of f dot, sorry, it is f dot s. Now when we remove the dot product by taking cos 180, That's how we are getting the minus sign. Okay. That's why we are getting this.
Oh, got it, sir. Okay.
Kushi, you understood
Okay,
why
okay.
negative sign is coming now? Yes? Okay, good. Okay, so these are the simple cases of calculation of work done by using the dot product when the force is constant, whereas by using integration when the force is variable. Okay. Now, next thing we'll see something very interesting, the relationship between work and kinetic energy. We'll see that so first of all, what is kinetic energy? It is the energy of a body associated with its motion. Hence the term kinetic. So kinetic energy is the energy associated with the motion of a given body. So let's say a body of mass m of any shape is moving with a velocity v, then its kinetic energy is given by the term half mv square. It's a subtopic of the same chapters actually. Okay? And here we are actually discussing about the relationship between work and kinetic energy. Okay. So kinetic energy is given by this formula, and the definition of kinetic energy is that it is energy associated with motion. So kinetic energy is also expressed in joules. Okay, so if mass is in kg, velocity is in meters per second. You can see that 1 joule is equal to half kilogram meter square. Sorry, is equal to this. Equal to 1 Newton meter. It's one and the same thing. So notice that work and energy have the same unit. Now, if a number of forces act on a body, then the net force acting on it, we know, is equal to mass into acceleration, where this net force is the sum of all the external forces acting on the body. So the net work done by all forces, that is that becomes this. Now acceleration can be written as rate of change of velocity, and ds can be written as velocity dt. So the displacement at any time is in a small time dt, the displacement is v dt, because instantaneous velocity is ds by dt. Okay. So that is why we can see that if we take the dot product of acceleration and displacement, we will get this, which becomes dv. So the net work done with this integration becomes ma dot ds integration, which further becomes mv dv integration. That's why we can see that if we are going from some initial state to some final state, the net work done is equal to initial to final. So like this, and hence this is called the final kinetic energy minus the initial kinetic energy, or the change in kinetic energy. So this is the relationship between work and kinetic energy, that the net work done by all forces acting on particle or body, it equals to the change in its kinetic energy. Okay. So by calculating the net work done, we can actually find the change in kinetic energy of body, where the kinetic energy is defined as half mv square. So the final kinetic energy is the value of half mv square at the final time. The initial kinetic energy is half mv initial squared, like that. So the change in kinetic energy is nothing but the net work done, or you can say the sum, the algebraic sum of work done by all the forces acting on a body.
Sir, once again, could you scroll up, please?
Yeah. This part. Okay, so this is clear now.
So just 1 minute.
Yeah, the concept is clear, I hope. So next lecture we will look at applications of this concept of work kinetic energy, and we'll see how to use this in numerical problems, that the net work done by the forces acting on a body is equal to the change in kinetic energy. All right. So that's it for today's session, people. Wish you all the best. Have a nice day.
Thank you, sir.
Thank you, sir.
So, sir, 1 minute, 1 minute, 1
So,
minute. Sir, 1 second. I was still writing that. Sir, okay.
Thank you, sir. Bye, sir.
Okay, sir. Thank you. Bye.
Okay, people. Bye then. That's it for today.